Back again. Part 3. Sorry about this. It's a lot of stuff. I think it's useful, but we'll see. Anyway, this part gets to the Lesage part, so I just figured that was worth commenting on. So, soon, coming up.
The atom can't move, the nucleus just sits there and everything's in balance, but there is this weak electric dipole force which is transferred through the body. And gravity cannot be shielded electrically because this dipole force, it's like a whole string of magnets. And if you have a string of magnets on a slippery surface and jostle them around, they'll all connect one to the other, a chain of them. And this is
right, but what's connecting them again? So I'm just saying that your explanation doesn't explain any of the dynamic, the actual mechanism that creates this association. And the association is really it's just gravity, and it's just once you label the gravity, red and blue, it can have a different effect based on whether it's red or blue. So again, with the magnet, what's happening is this regular gravity comes in and only one kind comes out. So it goes in both blue and red, and it comes out just red. And on the other side of the magnet, it comes in any color and it goes out just blue. And the consequence of that is that gravity is exactly the same. It just did exactly the same thing as it always does. But if it comes in contact with some other element that's sensitive to red and blue, so like steel or copper even, something that's not capable of being magnetic, but it's sensitive to magnetism in a sense, somewhat sensitive, it will have an effect. Particularly with steel, we'll just say some unmagnetized steel, its effect will be is that it's going to be sensitive to that polarization and react. How best to put that? That's probably better for another conversation. But anyway, yeah. So let's just get to it. But I mean, it's all the same. It's the same stuff. It's just subtly different versions of the same stuff, and it's not that you don't need that much range of difference to create all the difference. Like the primary colors create all the colors. Just 3 colors create all the colors. It's these little bits of change can create can have a lot of variation just based on the intensity of how that change affects other things. Good enough way to say it, I think.
exactly the similar process here. Now, here we go. Gravity has 2 poles like a bar magnet. And this answers the question about why is gravity always attractive? It's because we stand on the surface of the Earth. And this is the 3rd step on the path to discovery.
Yeah, well, this is the part that just doesn't make much sense to me. We already know that the Earth is both gravitational and magnetic, and to magnetize gravity in this sense, it just kind of doesn't seem right, because how is this gravity then affecting the magnetosphere and all the rest of that stuff? So it just doesn't intuitively make sense to create this electrical force to try to convert gravity into electricity. Like I said, it makes much more sense, I think, to start with gravity and explain how gravity is manifested into electricity and magnetism. Going the other way doesn't work.
Gravitationally induced atomic dipole set up an internal gravitational field that is weakly repulsive. You've got all of the positive ends of these dipoles facing one another inside the Earth. So on stars and planets, the attractive force between atoms is strong enough to hold these tiny dipoles in place. They can't fall. And so the internal pressure inside these large bodies, like planets and so on, is relieved. There is a kind of anti-gravity effect inside, and this is probably
yeah, well, again, but there's just no way to make this make sense. It's like if you went down into this how could it possibly, you would be electrically neutralized. So it just kind of breaks what what is known about how gravity works. Again, if I cut this sphere open, the interior here would have no electrical reality. That's even how electricity works, like gravity, is that if you hollow it out, there's no charge. So it's really just a surface phenomenon, and that's all it is. It's just, charge is a surface phenomenon. That's it. It's not going to be revealed any other way. You can, you can collect charge on a very thin metal, where you wouldn't be able to collect gravity on a very thin metal. If you couldn't make a gravity capacitor, for example, or something, because it just wouldn't work. Where charge, you can hold charge on plates, a lot of charge, a very strong gravity, so to speak, on a very thin foil. So how does that work? I mean, how can you analogize that to gravity, where we know gravity is quite dependent on this thick diameter to create the charge at this end, the force.
Down deep mine shafts don't conform to Newton's law.
Well, like I said, they do conform if you account for the fact that you're now boring into the gravitational mass, so you have to now extract from the equation all the mass above you. So if you're going down into the earth, you have to extract from the gravitation all this and call this essentially a separate moon on the other side of you. So all the mass that's on this other side of you, everything east or west of this line. Okay, so you kind of have to understand that that's the relevant factor. Well, it's even more than that, because you have angles that are very, very strong. These kind of angles. So the point is that you have to essentially extract from the equation this whole shield of exterior and break your circle down to whatever the distance is you're cutting in. So now you have a much smaller Earth on one side, and you have exactly on the other side of you a moon's worth of matter, and so your net gravity is going to be substantially less. So it's even, it's substantially less than inverse square, because you're not just shrinking. You're not taking mass out of the earth and not putting it anywhere. You're putting it above you, and so you're creating a gravitational entity above you that's going to change inverse square, because you have to compensate for the fact that you now have a moon over your head.
All stars and planets in the universe repel each other with an inverse square law force, because this is like a charged particle. It may have significance for understanding charged particles themselves. It suggests even lower levels of structure.
Well, again, the inverse square law, to me, the one that makes it the most obvious, is this visual one. So this fact that this hand, if I move half the distance closer, so I've cut the distance in half between my hand and you. The hand's 4 times as big. Now that visual fact, and it's the same for a shadow. That fact, that's gravity, and that's electricity. They both obey this rule because they're things functioning with this straight line idea. It's because light is moving in straight lines that these things are true. Kind of. I drew a picture. I'll have to, work on it. Yeah, it's kind of messy. But, the idea of using a cone as a way of illustrating the, instead of, you can use a square box, and I can just draw lines and show you how you can visually see how the proportions get bigger as you get bigger. But it's understanding that, circle areas also do the same thing, where, half change in the radius creates a 4 times change in the area. that kind of thing.
Now this is interesting. I mean, all stars and planets in the universe repel each other.
That one I just don't get. All stars and planets in the universe repel each other with an inverse square law of force. Where's that? A gravitationally induced atomic dipole set up an internal gravitational field that is weakly repulsive. Again, I don't see any evidence of that. Now, you see exactly the opposite, that the pole is exactly consistent with the inverse square, and there's no indication of some opposite force that's taking away from that fact. So I don't know what he's talking about.
Newton's attractive force has a limited sphere of influence.
Well, it depends on what you call influence again, right? You could say that a star is not influencing you. Okay, this little tiny speck of light coming to you. And it's the same as the gravity coming from that star. So you can sort of think about the idea that the gravitational influence is just as weak as the light influence. It's traveling the same path. But a photon is a photon. So the electron that little piece of light hits from a star, you know, and this little star, the light comes shooting at you. When it hits the electron, it's not a small event. It's a big event to that electron. So it's just that there are very few events, but the events themselves are significant. So yes, it's a small influence in the sense of the volume of influence, but the influence itself is just as strong as the photon. The photon from its source is just as strong as the photon 5 billion years away. The photon itself doesn't change. It's only how many of them are affecting you that changes.
This may explain many anomalies. In fact,
So yeah, so if somebody understood that, they could explain it to me, but I don't know what he was talking about here. Just no clue.
as I mentioned, the nines and towers and the fifth and sixth force, the complex structure and object.
You know, fifth and sixth force, the complex structures. I don't, so this again. Now we're adding more and more forces. Where I thought the plan was to keep it simple, is to reduce this to more simplicity, not to add forces, but to subtract forces. That's my indication.
Features of an inner core found inside the Earth by seismologists may have an explanation based on such a model. This is very recent. They found this odd structure to the inner core of the Earth.
Yeah, these are kind of vague references to something, so it's just not good enough as something I can comment on. But I just don't think there's any doubts that the Earth isn't full of marshmallow.
Part of the Earth, it's like the molecular force at a very low level. The fact that we're attracted to the Earth is the same process, but at a different scale.
So again, just to understand that the key difference, I just think is just kind of an obvious key difference, is that we sort of know that electric charge is kind of a surface phenomenon, that it travels along the surface of even conductors, and that's what can protect it. It can make conductors capable of carrying more than what you would think they could carry, is that they're carrying it almost on the on their skin. And all of that is defeated by this idea of what gravity is doing, which is a compression force. And charge isn't a compression force. It's almost the opposite. It's something looking to lightening itself to freedom, kind of a thing. It's not a compression force.
Was induced in us. The effects like that of an unmagnetized steel ball. We therefore assumed that gravity is always attractive. And also it's a mistake to assume that G measured on Earth is a universal constant. It depends on the polarization of the Earth itself. And that can be varied.
Yeah, so that's just talk in my opinion. I don't see any rational explanation of that. gravity is always an attractive force. Well, the argument is it's never an attractive force. Everything's all push, and the repulsive force that you see in magnetism is, again, just a pushing force where you've just created more pressure in a place that usually doesn't have pressure.
By adding or subtracting charge from the surface. The mass of a body varies with its surface charge. So when the thunderbolts of the gods were...
Right, so that's just, the mass of a body varies with surface electric charge. Your mass will vary based on your charge. Again, if I charge a battery, I'm putting quanta into it, and it will have a higher atomic weight because it now has more quanta in it. But that's in the only sense where charge affects mass. And in most circumstances, you're never going to be able to add enough charge to something to make significant changes in mass. I mean, some batteries you are, but I'm just saying that in most cases, it has to be a very good lithium or something for there to be a significant mass change.
Earthling around, and the planets were on orbits which meant that they came close to one another enough to exchange charge strongly. The masses were changing.
So again, I don't know what he bases that on, but he's just saying that when Venus and the Earth line up or something, there's a, whatever, invisible lightning bolts exchanging charge.
So if gravity repels, this is an odd idea, but it's not new. In fact, Newton considered it as a possibility because there was a theory which seemed to work. The pushing theory of gravity was originally proposed by Newton's colleague Nicolas Flatio de Douillet in 1690 and later by Georges Louis Lesage in 1748, a long time ago. They said that an omnidirectional flux of small particles permeates space and tends to push objects together. And because they mutually shield each other, it gives the effect that looks like gravity, and mathematically it works.
Yeah, well, it comes out that it does the inverse square thing because it's obviously doing the straight line visual thing. It's doing the same thing as this vision thing. And so it creates the inverse square rule of gravity's diminishing intensity. So it fits that. But I would argue that it does explain everything in the sense that it explains where the energy for this force comes from, where the expression of this force comes from. Again, there's no explanation in gravity. There's no evidence that the bodies themselves are creating the energy of acceleration. There's no evidence of the energy needed. Energy is always needed. Some sort of force is needed to move something, and there's no evidence of anything expending energy to create gravitational attraction. So it explains where the energy is coming from, and the energy is coming from that field of pressure.
It was known
and again, the key is the straight line vectors. You have to understand it as moving like photons in straight lines, and they don't go around corners.
The Flatio-Lesage theory was considered seriously by many scholars, including Newton, but it was discarded for very good reasons. If you have particles impacting a body, you're releasing energy, and the energy...
See, there you go, right? So that's his dismissal. His dismissal is if you have... And even, that's the catch of this, is they did make some effort to explain that in the sense that they used the terms like ultramundane particles. And the idea was these particles go through you, and it's only a certain percentage of them that affect your matter. And, not all of them. So most of them go right through you, and it's only a percentage of them that you catch onto, that they're grabbed, that are extracted out of this gravitational pressure. But I mean, the key word would have just been if they could have understood the concept of frictionless. There's no friction in nuclear function. So if they understood this force, if they could understand the atom and understand that the interactions would be purely kinetic, then they'd understand there's no such thing as heat. If everything's moving the same speed and everything's the same size, there's no heat.
Keep the Earth in orbit around the sun.
I mean, if all you're exchanging is direction, again, that's the argument here, is that the matter is already made up of a bunch of stuff with directional identity. And all the gravity's doing is saying, this is your new directional identity. I'm imposing a change in your directional identity, and now you will gain velocity that you'll be able to keep if some other force doesn't take it away from you. Because I'm going to exchange it. I'm going to exchange what you are with this gravity, and you're going to become gravitized, and that's going to create velocity. That's all there is. That's the effect. And again, the whole effect is caused merely by so the other thing doing that, absorbing direction that would have hit you, that isn't hitting you because it's absorbing it. It's gaining acceleration towards you, and by gaining acceleration towards you, it ate that direction. And now you can't feed on that, but you have a bunch of that opposite direction hitting you from behind that's going to push you, and that's going to accelerate you. And as you accelerate, you eat the direction that the other body would have gotten. And now it doesn't get it. And now it, is going to move towards you. See, that's the induction. The acceleration becomes mutual, and once the acceleration is mutual, there's the game. And so you could, we don't see the Earth accelerate, but it actually does. The pieces, atoms inside of the Earth are right now accelerating towards me. They're moving. That's why the Earth stays hot. And that's, is because there is stuff moving, accelerating towards me, just as my mass is accelerating towards it. And we're doing a lot of this bouncing in this tension we have. Again, my mass and the gravity of me is my acceleration is being pushed right through the chair, right through the floor, right into the ground, all the way to the center of the Earth. It's doing it.
Been enough to vaporize it. However, more recently, catch up here, Halton Arp, also known as the modern Galileo, discovered intrinsic redshift of quasars, and Anna's talked about that.
Right. So intrinsic redshift of quasars is something I might want to, I might want to look that up. But these are the things way out in deep space, so to speak, and they always seem to be redshifted. And so his argument, I suppose, is that the redshift isn't necessarily associated with velocity. I don't know if that's true or not, but whatever. Continuing.
He came up with, once you get rid of this redshift equals speed of recession, which gives you the distance, once he got rid of that, he found out that the universe was fairly static. But then he had a problem. If it's static, how can that be so? If gravity is an attracting force, everything should be falling in towards one another. But we don't.
Right, and everything is, but at the same time, the force is coming from all directions. There's no center to the chaos. So, it's not all coming from one direction. It's coming from all directions. And that just means that every little space in space has an equal directional pressure on it. So that's why every atom is semi-stable, is because every atom is just a place in space. And theoretically, the entire field is always got stuff that will be pointing to that vector. That's what the randomness creates, is that you'll have a perfect balance, so to speak. And what affects that perfect balance is other material objects around that atom that are going to block pressure from certain directions. But the idea of the inevitable pressure, a point in space does not mean that it only gets pushed from one side. It's, again, being pushed from all sides. So you have to understand, that's the premise. The premise isn't that the whole thing is a collapsing universe. The premise is that it's a chaos in some kind of container, a pressure container. And maybe that's just has to do with the, again, whatever the circumstance of the Big Bang was. If the Big Bang had a crust, the crust would always still exist, and the crust has been reflecting the pressure, creating essentially the pressure through that reflection.
He didn't observe that. So he actually, as he said here in this paper, he had an observational requirement to consider what he called Lesage gravity, this pushing gravity. He said, for many years I never questioned the obvious fact that the masses attracted each other. The attraction was so blatant that it required no thought. And this, unfortunately, is the situation in astronomy right now. It requires no thought.
Yeah, I've read up on this ARP guy, I remember before. I'm not sure, but I think he's dead, but I'm not sure. You know, that, but again, the attraction is so blatant and it required no thought, but the idea is that obviously attraction can be understood as push. You know, it's just a wrong assumption. You have two choices. You can say, hey, it's being pulled towards me, or you can say it's being pushed at me, and we just chose the wrong one as a way of understanding, because I guess it's easier to see it as being pulled towards you than to see the thing behind it pushing it.
Thought. But then observations of galaxies and quasars forced me to accept the fact that extragalactic redshifts were primarily intrinsic and not the result of recessional velocity in an expanding universe. So he went on, it is interesting how the crumbling of one fundamental assumption can have reverberations throughout the whole underpinning of science.
Yeah, I wish that was true. I mean, I wish there was this way to break, to go back and say, let's restart from some other position and see where it goes, you know, redefining that position. So yeah, start with the assumption of push and see how far you can make push work. And that's all it required for me, was just to give it a shot, to say, I mean, I didn't know of Lesage gravity when I first thought of this. I just, you know, but I'm just sort of duplicating the same step. I'm just saying, well, how do you make this make sense? And so you have this idea of saying, how can I think about how something can move towards me? And if I think about it, the idea of strings pulling, well, that doesn't make any sense. But the idea of things hitting, that I can make sense out of. And so that's what I started with, was the idea that what if it was like invisible light that was hitting it, something external coming at it, because I couldn't come up with any justification for saying there's anything internal that's creating this acceleration. I couldn't think of any way to explain how I can create its movement, and I can create movement in some other body. I'm the Earth, and I'm going to create movement in the moon, and how I can do that without expending some sort of energy. So I said the rain, the idea of rain, or photons, or something out there that's pushing in, it just made obvious sense. And then when you think about straight lines, it makes even more sense, and then it starts to match things. I'm just saying, I just wish they would do a do-over and say, yes, we can make that work.
I have the greatest respect for that man. He was prepared to go wherever the observational requirements led him. The sign of a real scientist. This is the Hubble Ultra Deep Field.
Yeah, I'm not sure. I think he said some other stuff that wasn't so scientific, but this is my recollection. But you know, it's always that way. You know, it's, you know, you get some stuff right, you get some stuff wrong. Except for me. Yeah.
14. An exposure time of 600 hours. It's merely the visible part of what's pushing in on us. ARP showed that these faint redshifted objects are not distant objects necessarily. So even though this is a deep field, it doesn't mean that they're far away. This is just looking with very long exposure at things, the redshifted objects, and they are relatively close. They're mixed up with all of the bright nearby stuff.
Yeah, well, I suppose there's got to be some other ways to figure out how far away something is, you know, some sort of triangulation or something, I don't know. You know, so you know, look at it when the world is spun this way, and then look at it again spun this way, and you should be able to do some sort of, you know, angular blah 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 whatever. But anyway, regardless, it doesn't really matter to me. I mean, you know, I mean, they don't understand redshift anyway, and redshift being something that's created by the mechanics of atoms and electrons, and the redshift happens at the source, not in between the source and the destination. So, but anyway, so I think that's probably enough. So I'll keep this one brief. I don't think it goes anywhere good after this. I mean, I guess I could jump around a little.
In other words, there was no Big Bang. I mean, that Big Bang was just a religious rewrite.
Well, I don't think it was exactly that. There was evidence of it. Religion, there's no evidence. The Big Bang, there is evidence. So, blah, 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 blah.
So, astronomy has a massive problem. With repulsive gravity, collisions tend to be avoided. But the problem is for astronomy is that with attractive gravity, all you have is attraction, collisions, and explosions. That's why a Big Bang was necessary in the beginning. You'll notice in this picture too, there are no lightning bolts. That's a grave mistake.
Yeah, I don't know how grave it is. I don't know. These probably could be considered sort of lightning bolty. You know, but whatever. You know, to think that that is a instrumental to the function of the crash, you know, is the lightning bolts. Again, I think it just, well, it's not silly, but I mean, it's sort of silly. Yeah, there's no, electricity is not holding galaxies together. Gravity's doing that.
Is there a method to stabilize the chaotic nature of a many-body gravitational system? And this was alluded to also by Annis.
Is there a method to stabilize? You know, there's stabilize to what? A many-body gravitational system. That's what we have. There's limits to what gravity can do. You know, essentially, I've argued that if you make something a really big black hole, let's say, if you get to a certain kind of density, a certain level of blockage, so you're blocking so much gravity, you're so thick that no one with the gravity can get to the center, the chemical pressure won't be enough to keep the atomic structure together, and it will explode. It'll supernova because it's the interior atoms will lose their coherency because gravity is what's holding them together. So again, it's like we talk about gravity as if it's a force, but it's really, it's, you know, it's this inverse thing. Its significance is really realized when it's absent. When you degrade gravity is when you see something happen.
What happens to orbits if we vary the mass of a planet electrically, remembering the dinosaurs and the sudden change?
Well, whatever. You know, the sudden change has been accounted for by a lot of things, and I don't think it makes any sense to say there was less gravity and therefore animals could be bigger, because I don't think less gravity would make the atmosphere easier to fly in. It wouldn't create enough density and things like oxygen, and so I mean it doesn't make a whole lot of sense, I don't think, to think that you could have a planet Earth with significantly less gravity that would have significantly abundant life forms.
Well, as we've seen, and with the Birkeland currents and so on, we can transfer electric current.
I mean, I suppose it would be evidence in some other geological record also, in some more dramatic way, in just how sediments formed, you know, things like that. I mean, you wouldn't be able to make a Grand Canyon, for example, I guess, if you had less gravity.
Through plasma.
I mean, water would lose its friction ability.
And, of course, the solar system is bathed in the solar plasma. And here the electric universe model meshes with the plasma universe and all of the peer-reviewed literature.
Okay, so this is all, you know, plasma universe. I mean, is this stuff really, is that good enough? I don't think that's good enough. Bathed in plasma. I don't think we're bathed in plasma. We're bathed in radiation, and our atmosphere blocks it. But, I don't know, plasma?
Yeah, on plasma cosmology. Now, I've presented this in more detail, and it's available on YouTube, so I won't go into detail here, but the idea is to show that the radius of the orbit of a planet of mass, say M1, changes with the radius and the mass are proportional for a constant orbital energy. That means that if the mass of a planet via, say, an electrical discharge, thunderbolt of the gods, was to double, its orbit, the radius of its orbit would double, it would move out. And this is important because you can...
Yeah, well, you say, but I don't think that's true at all, because you'd have to definitely change the velocity. So if you change the mass of the Earth without changing its velocity, it's not going to move out, it's going to move into the sun. So I don't think you're correct.
And then establish order out of chaos. Now, in the case of Venus, they've already detected these strings.
I mean, I have to think about it for a second. I mean, the Earth is, the mass, yeah, no, the mass is irrelevant. You're correct. Okay, so from the sun's point of view, the mass of the Earth is irrelevant. The sun is going to create a certain amount of, is going to block a certain amount of gravity. And that's what it's going to do. And it doesn't matter what the mass of the stuff is out there, except in the sense of what it's going to block and force the sun to move, but that's going to cause the sun's activity, not the Earth's activity. So, yeah, theoretically, if you double the mass of the Earth, yes, it will now have a greater momentum, you know, velocity times mass, a force, and so it will eject itself to a wider orbit because it'll have more energy to do that. Right. Well, whatever. I have to think on that one. But regardless, it doesn't have anything to do with the subject, I don't think. Yeah, I really don't.
Things, in other words, Birkeland currents, flowing between Venus and the Earth during conjunction there. In other words...
Yeah, so this is where he's making this argument that there's some kind of thing going on between the Earth and Venus when they're lined up, at their closest proximity, and that you, theoretically, if you made them even closer, that somehow you'd have even more or something or other. So I don't know why we aren't exchanging sparks with the moon. But regardless, it doesn't... it's gravity. There's no electricity on... on that size of the universe. Electricity is out of the game altogether. Electricity is just a manifestation of gravity.
That tail you see behind Venus has been detected by a spacecraft. I can't remember which one it was.
Right, but the fact that there's a consequence to us having gravity and Venus having gravity, you know, and there'd be there would be some magnosphere, whatever, radiation exchange, yeah, okay. But does it mean anything? Is it significant? Does it change anything substantially? Do we feel Venus lift us off the Earth? No.
Decades ago, I think this was back in the 1980s when it was reported. Now, in the electric universe, each planet is a small cathode in the solar discharge, and the electrons are actually transferred from Venus towards the Earth. It was the SOHO spacecraft, by the way. So the Birkeland currents transfer electrons from the inner planet to the outer one. The result is to increase the mass of the outer planet. Remember,
Right, so he's saying that somehow when this happens, Venus actually gives us mass, and I don't think there's any evidence of that whatsoever. Whatever. Yeah, like I said, this doesn't really go anywhere interesting, in my opinion. I'll just jump ahead a little bit. Probably going to play an ad or something. Come on. Just give up. Anyway, yeah, I've really done enough. So till next time, and until the next thing I can find a comment on, I suppose, or, well, I'll see where I go, see what I do. Maybe I'll do the magnetism thing again, draw some pictures and whatnot. But we'll see. So, thank you to those who hung in there and indulged and whatnot. Sorry.